Welcome back, everybody. This is our video solution to problem 5, our final problem from quiz 4, here in fall 2023, Math 307, Linear Algebra at Cal State Fullerton. And this extremely long problem is all about the vector space axioms. So let's dive into it. We start with a set V, which is going to be the real numbers along with some extra value. Okay, so we're using here the Greek letter omega. So this is just something extra. It's not a real number, it's just something we're adding to the set. And we want to define two operations, a binary operation as well as a scalar operation. So the binary operation, which you're giving here, we're going to call this O plus, all right, because, well, that's the LaTeX command for it, O plus. It says if you want to add two real numbers, A and B, it's just actually the regular addition. If, however, you want to look at a real number O plus this extra symbol omega, well, it doesn't matter which order you do it in, you're going to get back the real number you started with. And then finally, if you're going to O plus two copies of omega together, you just get omega again. All right, so here's some more explanation of it, right? This O plus is the normal addition of real numbers, but we're extending it to include addition with omega. All right, now we have our scalar operation, which we'll call O dot, right? Again, based on the LaTeX command. So here we need an operation which takes a real number and then something in V, and it returns something in V. So I can take some alpha, which is just going to be a real number, and if I multiply it, well, actually by some other real number, B, it's just going to be the usual multiplication of real numbers. But if I take alpha and take O dot with omega, I'm again going to get omega. Now you might say, well, why haven't I done omega O dot omega? And that's because our scalars are just the real numbers, not all of V. Right? Remember, we need a field here, and we don't have any clue about whether or not this V would be a field. Okay, fine. Yeah, more explanation, just saying what I said. So let's move down into the problems. It says list all of the vector space axioms using the notation of this set V along with the O plus and the O dot using R as the field. And so then there's an example given. You can see this looks like our normal distributivity axiom, but we have an O dot and an O plus where we would normally have a regular dot and a regular plus. All right, well, so let's try to write down our vector space axioms in this context. All right, so first, we're going to have the associativity axiom. So we have additive associativity. All right, and so what does that tell us? It says if we do a triple set of numbers, right, or things from V, so if I have, let's say, U, V, and W, not omega, but W, in V, then this implies that if I do U, O plus V, O plus W, well, now there's a question. Which do I O plus first? So what if I do the U and the V first? All right, well, somebody else might say, I wanted to do the V and the W first. And associativity would say those are the same. All right, so next we have additive commutativity. So this is where we have U, V, and V. If I do, I don't need a parenthesis there. If I do U, O plus V, this should be the same thing as V, O plus U. Okay? The addition commutes means it doesn't matter which order you do the addition in. All right, next we need an additive identity. Right? Oh, of course I've been writing plus here. I should be writing the O plus. So the additive identity would say there exists some element, okay? And we usually call it 0, but I don't want to call it 0 right now because we have a 0 in the real numbers, and we haven't established that that's actually going to be the 0 here. So I'll just use the letter Z, right? First letter of 0. So there exists some Z in V such that for all U in V, we have that Z plus U is equal to U plus Z is equal to U. So we have an additive identity. You can add it to anything, and it doesn't matter. And of course, we're using the O plus. All right, next we need inverses. Okay, so these are additive inverses. So this would say, for all u in v, there exists something which, again, I don't want to make it seem like we're using the actual negative, because that may not be the right thing here. So I'm going to write down u to the minus 1, not to confuse with the field axioms, but just to say it's some sort of an inverse, right? So there exists some u to the minus 1 in v, such that u(O) plus u to the minus 1 is equal to u to the minus 1 O plus u is equal to the additive identity, which is z. Okay, so this is a list of all the axioms that build up the structure just using the addition. So now we need to start bringing in the scalar multiplication. So our first one is we have our O dot identity axiom. And so what that means is if I take the identity in the field, which remember is R, we know what the identity in that field is. It's 1. So if I take 1 and I do O dot U, right? So here u is in v. This is supposed to equal u. All right, so there's that axiom. And it turns out, right, that in terms of just using these scalars, there's only going to be 2, so we just need one more. And so the other one is our scalar associativity. So what does that say? Well, that means if I have multiple elements of the field, so for here, for all alpha, beta in R, and okay, I guess I'll take some u in v, we have if I take alpha, beta, u, and I first say take the dot of beta with u, that'll give me another element of v, and then I take the dot of alpha with that element. Or alternatively, I first just multiply alpha and beta together, right? This is just happening in the real numbers. It's regular multiplication. And then I O dot that with u. All right, and the associativity axiom here says you get the same value. All right, so that's all the stuff with the scalar multiplication. Now we need the one that bring them both together, and that's our distributivity axioms. Now I actually already gave you one, right? So you have one of those axioms right here, right? It wasn't that nice. So this axiom is the one where I'm going to be distributing a scalar over a sum. The other axiom, right, so I can just drag this one in. The other distributivity axiom, right, and notice I said here one of the distributivity axioms, right? So the other one is going to be if I distribute a sum of scalars over a vector. So if I have alpha plus beta dot u, so here alpha and beta are in the real numbers and u is in our set v. And in that case, I would get alpha dot u O plus. Okay, so now this plus is happening in v, so I have to use the O plus alpha dot, beta dot u. And we'll put some parentheses in here to make it clear what's happening. All right, so that's what our distributivity is going to look like. All right, so that answers part A. Now, we have not established that any of these things is actually true for our given structure. We just wrote down what the axioms would look like. So in part B, we're told to determine the additive identity of V, which is one of these axioms, right? Is that there is some additive identity. So we're looking for something that we can add to anything in V, and it won't change that value. So let's see. Let's go up to our definition. The first thing is that if we do two real numbers and we take their O plus, it's regular addition. And we already know what the additive identity is for regular addition, right? It's 0. But there's this omega, right? This omega is in the game. So let's see what happens. What if I did 0 plus omega, right? So 0 O plus omega. Well, according to this rule, it's actually 0. Oh, how interesting. this is telling us that 0 is absolutely not the O plus identity of V. In fact, this omega is the O plus identity. Because what does this do? If I take omega with anything in the real numbers, it just gives me back the real number. And if I do omega with itself, I get omega. So in fact, omega is the O plus identity. How bizarre. All right, the last problem says it turns out that V is close to being a vector space, but it's not a vector space. Oh, wow, how disappointing. And then, amazingly, exactly one axiom fails, right? This is crazy. If you check all of these, right, only one axiom is going to fail. And we need to find that axiom. Oh my goodness. Okay, well, here's my guess right from the beginning. Because the identity has changed, that makes me think I should probably check that there are inverses still, right? That's a big change that we made, so I want to start there. And if it's not that, I'll check some of the other stuff. All right. So let's take a look. Can we get additive inverses for every element? Now, I already know that if I add, say, real numbers together, I can get 0. But remember, I'm not trying to get 0. I'm trying to get omega. Well, do we have anything up here that allows me to add things together and get omega? Well, the answer is yes. This bottom line allows you to add omega to omega, and you get omega. So certainly omega has an additive inverse. But what if I don't have an omega? What if I just have a regular old real number? If I add it to any of the other real numbers, I just get a sum of real numbers. That's definitely, right, not equal to omega. And if I add some a to omega, I just get back a, which is also not equal to omega. So in fact, the additive inverse axiom fails. So the additive inverse axiom fails spectacularly for all a in the real numbers. Since, well, let's just write it out carefully, right? If a plus b equals omega, the additive identity, right? If I can somehow get the additive identity, well, from the rules, then this implies that a equals b equals omega, which is a contradiction because a is a real number and omega is not a real number. Okay, and there we go. That finishes it off. All right, we will see everybody next time.